Now we have already studied what is binding energy and the mass defect, okay, and how it relates to the strong force, everything, all of those we have already covered. So in this class, we will be solving a very simple numerical based on the binding energy and mass defect. And this, of course, is no need to tell you that this is very, very important concepts that we'll be discussing, and you can expect a question on this in your NEET or JEE mains. Okay, very, very important concept. So first, let us revise what is the mass defect. So these are the four nucleons, two neutrons and two protons. They have come together inside the helium nucleus, and in that process there is a reduction in the mass. There the net mass is actually reduced by how much? 0.03 AMU. Okay, AMU is the atomic mass unit, also known as Dalton dA. Okay, atomic mass unit or Dalton dA. So now let us, before we go further into energies, let us just see what 1 AMU is. 1 AMU is the 1/12 the mass of the carbon atom. 1/12 the mass of the carbon atom. And of course, this is the real mass. This is actually, if we weigh the carbon atom and then divide it by 12, this is the mass we will get. And this is nothing but 1.66 into 10 raised to power minus 27 kilogram. Okay, so this is the real mass, and therefore this has to have an equivalence in terms of kilogram. So that is the 1 AMU in terms of kilogram. Now, what is the next thing that we need to know in order to solve the numerical? So what is the numerical we are trying to solve? So there is a reduction in mass. This is the mass defect inside the helium nucleus. Okay, so we know that due to this mass defect, there is a reduction in the energy, and there is a net output of energy. Okay, and that is known as binding energy, and that binding energy is given by the formula EB is equal to the mass defect delta M C squared. Okay, this comes from Einstein's famous equation E equal to mc squared. So the mass defect, there is an equivalent, that mass defect produces an equivalent loss in energy, and that is known as binding energy. So if I bring all of these nucleons together, I lose, okay, there is a net output of energy EB that we get. In other words, if I need to break these nucleons apart, I would need to supply them with an energy of EB to break them apart, or the binding energy I would need to supply. So that binding energy, that is what we are trying to calculate. That is the net output that we want. Okay, so it is very, very easy. So this equation we already have. We know the value of C, we know the delta M. It is just some unit fudging that we need to do, and there is one more unit that we need to understand before we delve into this, which is typically used in measuring the binding energies. Okay, that is why we are coming there. It is the 1 electron volt. It is the unit of electron volt. And what is the definition of 1 electron volt? It is the net change in energy of an electron as it undergoes a change in potential difference of 1 volt. And of course, because it has the unit of energy, okay, it is nothing but the charge of an electron. Okay, it is nothing but 1.602 into 10 raised to power minus 19 joule. It is just numerically it is equal to the charge of an electron, of course, right? Because that is the definition. In the definition itself it comes, it is the net change in energy of an electron as it undergoes a potential difference of 1 volt. So that will come up to be 1.6 into 10 raised to minus 19 joules. So we have related the electron volts to joules, and we have related the AMU to kilogram. Now the first thing that we are going to do is we are going to calculate the energy EB per AMU. Okay, so if I have a mass defect of 1 AMU, how much energy would I get? Okay, so that is what we want to find out. So it is the 1 AMU multiplied by C squared. C squared is nothing but 3 into 10 raised to power 8 meter per second. So this is in SI units. Okay, so I need to convert this also into SI units. I can do that. 1 AMU is nothing but 1.66 into 10 raised to power minus 27 into, this is squared, sorry, into 3 into 10 raised to power 8, the whole squared, and this will come in joules. Now you can simplify this further. Nothing very complicated. We are doing everything very, very simply. Okay, this you can simplify this further, and what you will get is 14.94 into 10 raised to power minus this will get is 10 raised to power minus 11, and then there will be joules here. Okay, so that is the net binding energy per AMU. Very, very important. Okay, in joules, it is given in joules. Now, as you can see, joules is a very large unit for this binding energy, for the computations of binding energy. Why? Because this number is coming out to be very, very small. So typically binding energies are actually expressed in terms of electron volts, and that is what we are going to do here. We are going to convert this to electron volt using this formula. Okay, so go from joules to electron volt, we have to divide by this quantity, and that is what we will do. 14.94 into 10 raised to power minus 11 divided by 1.6 into 10 raised to power minus 19 electron volt. If you simplify this further, what will you get? You will get this 932.58. Okay, so that will be 932.6 into 10 raised to power 6 electron volt. Okay, now this 10 raised to power 6 factor I can actually lose, and I will get 932 mega electron volt. Okay, so this 10 raised to power 6 I converted to mega, and this is very, very important. It is the binding energy EB per AMU. If I lose 1 AMU, if the mass defect is 1 AMU, this is the binding energy that I will have. Okay, so this is something that we need to remember if we want to solve the numericals very, very quickly. Okay, in this case, since I have my AMU, the amount of mass defect is 0.03. Okay, that is the mass defect. Therefore, what would be the binding energy for helium atom? So the binding energy for EB helium will be equal to 932 multiplied by 0.03, and if you compute this comes out to be 27.9. okay, that is the binding energy, and of course this is in mega electron volt, so we always have to make sure that we write the units. Okay, so this is 27.9 or approximately 28 mega electron volt. If we want to compute for this helium the EB, okay, notice what I am doing, EB helium per nucleon. So per nucleon, okay, so per nucleon, that is what I want to compute. What would that be? That will be 28 divided by 4. That approximately comes out to be 7 mega electron volt. Okay, so that is the binding energy per nucleon. That will be 28 divided by 4 because there are total of 4 nucleons. So I have now computed the binding energy of helium per nucleon, and that comes out to be 7 electron volts. If you remember this chart, we saw this in the last class, and if you notice, for the helium, indeed the binding energy is equal to 7 mega electron volt. Okay, so we have solved one numerical successfully. This method, this number of 932 mega electron volt binding energy per AMU is very, very important. Okay, 932 mega electron volt, you should remember it. Again, the electron volt and joule relation is important. 1 AMU is equal to 1.66 into 10 raised to minus 27 kg. That is also very, very important. Another thing to remember is that sometimes AMU is not given in terms of AMU, but it is given in terms of Dalton or DA. Those two are equivalent. Okay, thank you very much.